On November 23rd, 2023, something extraordinary brushed past our planet. Something so subtle it distorted space itself by less than the width of a proton, yet so powerful it carried the signature of one of the most violent events in the universe. Deep within the detectors of LIGO, a faint ripple appeared. To the untrained eye, it was just noise. But to scientists, it was a message that had traveled for over 7 billion years. Two black holes had collided. Now, black hole mergers are no longer rare discoveries. Since 2015, when gravitational waves were first directly detected, astronomers have cataloged hundreds of these cosmic collisions. But this signal was different. It didn't just represent another merger. It challenged the very framework of how we believe black holes form, because the two black holes involved shouldn't exist. They belong to what scientists call the mass gap, a mysterious range where black holes are not supposed to form according to current stellar evolution models. And yet, here they were, massive, spinning, and real, leaving behind a gravitational fingerprint impossible to ignore. This is the story of how we detected the undetectable, uncovered the impossible, and began rewriting what we thought we knew about the universe. Across the cosmos, black holes often exist in pairs. Locked together by gravity, they orbit one another in a slow, deadly dance. Over millions or even billions of years, they spiral closer and closer, losing energy as they go. As their orbit shrinks, their speed increases until eventually, in the final moments, they are moving at a significant fraction of the speed of light. Then comes the end. In a fraction of a second, the two black holes collide and merge into a single, more massive black hole. But this isn't a quiet process. The merger releases an enormous burst of energy, not as light, not as radiation, but as ripples in space-time itself. These ripples are called gravitational waves. First predicted by Einstein in 1916 as part of his theory of general relativity, gravitational waves are distortions in the fabric of space-time caused by accelerating massive objects. Under most circumstances, these distortions are far too small to detect. But when something as extreme as a black hole collision occurs, the resulting waves can travel across the entire universe. By the time they reach Earth, however, they are incredibly faint. Imagine stretching and compressing space itself by a fraction smaller than a proton across a distance of several kilometers. That is the scale of change scientists must measure to detect a gravitational wave. For decades, this seemed impossible. Even Einstein himself doubted whether gravitational waves could ever be observed directly. The technology required simply didn't exist. That changed in 2015. The Laser Interferometer, Gravitational Wave Observatory, better known as LIGO, was designed to do the impossible. LIGO consists of two massive facilities located thousands of kilometers apart. Each site features two long vacuum tunnels, arranged in an L shape, with each arm stretching over 4 kilometers. Inside these tunnels, lasers are fired back and forth between mirrors with extraordinary precision. These mirrors are engineering marvels, suspended by ultra-thin fibers and isolated from even the tiniest vibrations. They are polished to near perfection. The system is so sensitive that it can detect changes in distance thousands of times smaller than a proton. Here's how it works. A laser beam is split into two and sent down each arm. When the beams return, they recombine. If the lengths of the arms remain unchanged, the light waves cancel each other out in a predictable way. But if a gravitational wave passes through, it stretches one arm while compressing the other, ever so slightly. This tiny distortion changes the way the light recombines, producing an interference pattern that scientists can measure. That's how we see gravitational waves, not with telescopes, but with precision instruments that measure the shifting geometry of space itself. Since its first detection, LIGO, alongside partner observatories, has identified hundreds of black hole mergers. Each signal tells a story: the masses of the black holes, their spin, their distance, and the nature of their final moments. But the signal detected in November 2023, known as GW231123, stood out immediately. It lasted only about a tenth of a second, but it was strong, far stronger than typical background noise. At first, scientists were cautious. Instruments can glitch, data can mislead. But when the same signal appeared in both detectors, separated by thousands of kilometers, it became clear this was real. To be certain, researchers ran extensive statistical analyses, simulating thousands of years of fake data to see how often random noise could produce a similar signal. The result? The odds were less than 1 in 10,000 years. This was no accident. This was a genuine event. Once confirmed, the next step was to understand what caused it. Scientists compared the signal to a vast library of theoretical waveforms, simulations of how different black hole mergers should look when detected by LIGO. Each waveform acts like a fingerprint, allowing researchers to match the signal to a specific type of event. The best match revealed something astonishing. The collision involved two black holes with masses of approximately 103 and 137 times that of our Sun. When they merged, they formed a single black hole with a mass somewhere between 182 and 251 solar masses. That alone was remarkable, but it was only the beginning. These black holes were also spinning at incredible speeds, close to the theoretical maximum allowed by physics, and most importantly, they fell squarely within the mass gap. To understand why this is a problem, we need to look at how black holes form. Most black holes originate from massive stars. When such a star exhausts its nuclear fuel, it can no longer support itself against gravity. Its core collapses, triggering a supernova explosion that blasts away the outer layers. If the remaining core is massive enough, it continues collapsing until it forms a black hole. This process works well for stars up to a certain size, but for extremely massive stars, those between about 130 and 250 times the mass of the Sun, something different happens. Instead of collapsing into a black hole, these stars undergo what's called a pair instability supernova. In this process, the star becomes so hot that energy is converted into matter-antimatter pairs, destabilizing the core and causing the entire star to explode completely. No core remains, no black hole is formed. This creates a gap, a range of masses where black holes shouldn't exist. And yet, GW231123 revealed two of them. So how did they form? One possibility is hierarchical mergers in dense environments like star clusters. Black holes can collide and merge multiple times, gradually growing larger. Over time, this could produce black holes within the mass gap. But there's a problem. Each merger tends to randomize the spin of the resulting black hole. Over multiple mergers, the spins should average out, producing relatively slow-spinning objects. The black holes in GW231123, however, were spinning incredibly fast. This suggests a different origin. A newer hypothesis points to something often overlooked: magnetic fields. When massive stars collapse, they don't simply vanish. The aftermath is chaotic, a swirling cloud of gas, debris, and energy surrounding the newborn black hole. If the original star was rotating, This material can form an accretion disk around the black hole. As matter falls inward, it transfers angular momentum, causing the black hole to spin faster. Now add magnetic fields into the mix. These fields can become twisted and amplified within the disk, generating powerful forces that can eject material away from the system in the form of jets. This process does two important things. First, it removes mass from the system, preventing the black hole from growing too large. Second, it can influence the spin, either accelerating or moderating it depending on the strength of the magnetic field. In certain conditions, this mechanism could produce black holes that sit precisely within the mass gap, while also spinning rapidly, exactly like the ones detected. Simulations have shown that stars initially as massive as 250 solar masses could lose a significant portion of their mass before collapse, ending up just above the mass gap. After the explosion, magnetic interactions could further shape the final black hole's properties. Even more intriguingly, these processes could generate brief but intense bursts of energy, similar to gamma ray bursts that might be observable with current or future instruments. If such signals are detected alongside gravitational waves, they could provide crucial evidence supporting this theory. What makes this discovery so exciting is not just the detection itself, but what it represents. For years, the mass gap was considered a firm boundary, a rule of nature. Now it appears to be more like a guideline. If black holes can exist within this range, it suggests that our understanding of stellar evolution is incomplete. There may be additional pathways to black hole formation that we have yet to fully explore. It also raises a tantalizing possibility. The universe may be filled with hidden populations of intermediate mass black holes waiting to be discovered. Gravitational wave astronomy is still in its infancy. In just over a decade, it has transformed from a theoretical concept into one of the most powerful tools in modern astrophysics. Each new detection expands our understanding, revealing phenomena that were once beyond imagination. GW231123 is a perfect example. A faint ripple, traveling billions of years, has forced us to rethink how black holes form, how they evolve, and how extreme the universe can truly be. And this is only the beginning. Future detectors, more sensitive and more precise, will allow us to observe even more distant and subtle events. We will detect smaller mergers, larger ones, and perhaps entirely new types of cosmic phenomena. With each signal, we are not just observing the universe, we are listening to it. Somewhere out there, right now, black holes are colliding. Space-time is trembling, and waves are spreading outward in all directions, carrying secrets across the cosmos. One day those waves may reach us, and when they do, they may once again reveal something we thought was impossible.